Hello everyone, my name is Tian from EPFL. I'm going to present our paper titled The Least Increasing Aversion Protocol Illustration on Identifying Individual Susceptibility to Cybersickness Triggers. I think everyone here today know more or less about cybersickness, so I'll skip the introduction. We know that cybersickness is problematic. First of all, in typical VR games, there are a lot of factors interplay with each other, and these factors could lead to different symptoms. Each symptom may have many possible causes. So each individual could show different responses to different VR environments. Also, the cybersickness reduction techniques could have varied effects due to individual difference. For example, as a very sensitive individual myself, the famous FOV reduction techniques and rest REMs are not working for me. And even with teleportation, I could be sick after playing a while. So the main topic here we want to focus today is individual susceptibility. We found that the research on individual susceptibility have mainly focused on demographic factors like gender, age, or past experience such as history of motion sickness or previous experience with games or VR. And however, one area that has not been studied enough is how different people react to different cybersickness triggers. Well, some participants may experience cybersickness mainly due to factor A, and others may be more affected by factor B. The question is here, is there a way to characterize individual susceptibility? Previous studies have mainly focused on a single dimension of measure, the overall level of cybersickness. But is that enough? Could we develop a more comprehensive method to identify key sensitive factors for each individual and rank these factors based on their level of impacts? To address this challenge, we introduce a new protocol called Least Increasing Aversion, short as LIA, which is inspired by the subjective matching techniques protocol previously employed in virtual reality to ascertain the comparative significance of multiple factors for individuals. This protocol measures two key dimensions of individual susceptibility. The first one is sensitivity level, which is the intensity of cybersickness an individual may experience. The second one is the cybersickness triggers, which specific factors contribute to their different discomforts. The primary goal of LIA is to determine the order in which different factors triggers cybersickness in an individual, helping us to understand which factor have the greatest impact. Why do we need LIA? Before diving deeper into the protocol, let's recall an important point. Cybersickness in VR can be influenced by multiple factors. One traditional approach to study all the factors is using a full-factor design. However, this method requires testing every possible combinations of factors, leading to extremely large and time-consuming experiments, especially when multiple factors are involved. Furthermore, cybersickness is an unpleasant experience, and highly sensitive individuals may struggle to repeatedly endure such discomforts. Yet, to fully understand susceptibility, it is crucial to include these individuals in our studies. This is where the LIA protocol comes in. It provides a structured way to identify and rank the most influential cybersickness triggers, while minimizing the unnecessary exposure to discomfort with minimum sessions. Due to our time constraints, we have to skip the detailed explanation, but using an actual experiment later on. However, our paper provides a thorough theoretical introduction to LIA protocol and how to apply the LIA protocol in practice. Now let's see an actual experiment adopting the LIA protocol. In this experiment, we introduce three factors: the row axis rotation, yaw axis rotation, and pitch axis rotation. And each factor has two levels. Level 0 means no effect, and 1 means maximum effect. Following the LIA protocol, the first session in LIA is to introduce all the three factors at their maximum level. This means that the participant experience the most extreme version of VR environment, where all the factors are set to level 1. This serves as a starting point to observe the participant tolerance under the most challenging condition. If they experience severe cybersickness, we know that at least one or more of these factors is a strong trigger. Next, in session 2, we take the opposite approach. In this session, all the 3 factors are turned off, meaning the participant experience a relatively neutral VR experiment. This helps us establish a baseline, so we can later compare how different levels of these factors impact an individual's discomfort. If the participant still reports discomfort in this neutral condition, it could indicate a more general sensitivity to VR or existing factors inside the scene. Once we have both the worst-case scenario and the baseline, we start gradually adjusting the VR conditions by step introduce the triggers. In each new session, the participants have 2 choices. The first choice could be introduce a new factor that I find least sick. The second choice is increase the level of an already introduced factor, but without reducing it later. So in the third session in our experiment is a session with only one axis rotation. The choice of which rotation axis is based on participants' own selection. Similarly, the fourth session is a session with 2 axis rotations. Due to the time constraints, again, we have to skip this game demo. Please take a look in our paper page if you're interested. Eventually, we have 35 healthy human subjects, 18 females, age range from 20 to 45 years. Completed all 4 sessions. Here we present the paths chosen by the participants. Each color indicates a selected path during the experiment, and the number represents the probability of the selected path by the participants. The first digit is a yaw axis. The second digit represents pitch axis, and the final digit represents roll axis. The black numbers above the black circle and the color lines represents the percentage of participants who enrolled in this path. The graph on the right side summarizes the probability of the path is chosen. It's not difficult to see that we have a majority of participants who are role dominant with yaw axis as the least sick axis. We further plotted the total SSQ scores distribution over sessions. Error bars represents the standard deviation. And when we compare the results from session 1 and sessions 3 and 4, it is not difficult to conclude that with the LIA protocol, we could find the dominant rotation axis for each individual with a possible selection of individual preference. The SSQ are applied before and after VR exposure, and it doesn't reveal the real-time discomfort during the VR. Hence, in order to get more information, we also did the analysis of the FMS. It is worth noting that the susceptibility of individual turns out to be more intricate and multifaceted. By closing analysis, the graph of the longitudinal strategies of each participant, we discovered 4 distinct participant groups with varying susceptibility considering both cybersickness triggers and severity levels. The first group displayed immunity to all rotation factors, indicating that the presence of the individual were resilient to rotations. Understanding the mechanism behind this immunity could inform strategies to mitigate cybersickness for a broader population. The second group consists of individuals highly sensitive to a specific factor, suggesting that certain triggers can significantly affect their susceptibility to cybersickness. This finding raises the possibility to identify this trigger and developing personalized intervention to minimize cybersickness in these groups. The third group consists of individuals who are sensitive to 2 factors, illustrating the intricate nature of the individual susceptibility. The final group exhibits an equal sensitivity to all rotation axes. Recognizing this group is crucial for targeting interventions and designing virtual experience that cater to their needs. While the least increasing aversion protocol offers a structured approach to studying cybersickness. It also comes with certain limitations. First of all, the experiment duration in LIA protocol wasn't specified. Our goal later is to investigate a shorter 15-second version to make LIA more practical and efficient. Secondly, since the nature of LIA is to investigate multiple factors and levels at one experimental settings, as the number of factors increases, the number of sessions required also increases, which can make the study more time-consuming and demanding for participants. However, the normal VR game setting often involves multiple factors, hence LIA aims to provide an easier way to access as many factors as possible at once to help find out the dominant factors for individuals. By the end of the LIA protocol, we could obtain a personalized ranking of cybersickness triggers for each participant. This information is very useful because it allows us to tailor a VR experience based on individual needs. Instead of applying a one-size-fits-all model, we can identify and rank the most relevant factor or factors for each individual, making VR more accessible and comfortable for everyone. So in the future, it can be extended to optimize VR experience based on individual sensitivity profiles and help in designing adaptive VR environment that reduce cybersickness. Thank you for your attention.